is satisfied for some suitable values. Yes, somebody has raised hand, please.
सर आपकी आवाज़ लैग हो रही है थोड़ी और ये पीपीटी भी लैग हो रहा है.
I'm really sorry because today I'm in home. I can't help it about the network connection. Once the condition of IB greater than IB minimum is satisfied for suitable values of input voltage, Vi equals to V high greater than or equal to V min, the transistor will work in saturation region with constant collector current IC equals to IC sat VCC by RE. Tentatively, this is the condition, or if you have to maintain a proper saturation region without any failure, so usually then we take a thumb rule. The base resistance is usually taken 10 times higher than the value of the collector region to drive transistor into hard saturation region. Hard means quite active saturation region. For any input Vi greater than equals to VBE sat and Re not equals to 0. So these 5 or 6 are quite important design rules which we have to always keep in mind while we are designing a transistor as a switch. However, after the theoretical calculation, then we have to done the simulation, and depending on the simulation, if we can satisfy, cross verify that the ranges, because the theoretical calculation always gives the input signal Vi for a range of values of input signal, a range of values of RB minimum to RB maximum, IB minimum to IB maximum. Then you have to do the simulation to narrow down or to cross verify your theoretical result. And after that, once you are cross verified through your simulation that the range whatever you are projecting is more or less fine, then actually you have to jump for the practical experiment. However, doing the practical experiment and simulation, there are a hell lot of difference, because in case of a practical simulation, whenever you put different kind of resistances, metallic wires through the breadboards, everything will become interconnected through the electromagnetic interference. I do not know while studying your electromagnetic spectrum you have studied about the electromagnetic interference or not. The electric field, when there is a flow of the electric field through any metallic wire, that also creates certain magnetic field, and those electric fields and magnetic fields will interfere with each other, so that actually becomes as, or that intrudes as a noise. Whenever such noise elements increases, definitely the output gets too much fluctuated, or a proper data cannot be measured through your CRO or through your DSO. So simulation only provides or your narrows down of the choice of the design rules. However, then further the actual practical struggle starts while doing the experiment. Now, when we are talking about the transistor as a switch, while we are doing the transistor, obviously what should be our motive? Our motive is not only to bypass the actively region, that is from to jump from cutoff to saturation region by jumping directly and bypassing the active region. That is our motto, as well as how fast you can do that. This jumping, how fast you can design a switch, that is also becomes one of the measuring performance parameter. If your switch is lagging too much even after putting the switch on, then definitely no one is going to buy your product. So that depends, or tremendously depends on the next subsection. What actually defined is the transistor switching times. How less and less switching times can be governed. Although the switching times depend on many factors, this subsection will analyze the performance of the transistor switching times and its different consequences. Let's have a typical transistor switch and the input we are going to provide on that transistor switch. So this is a simple transistor switch circuitry where you have provided your VI. Sorry, I should write. Oh, so this is your input is applicable. This is your VBB. This is your input base resistance RS. The current IC is flowing. This is a typical transistor circuit, the load resistance RL and the VCC, on which you have been provided an external signal. Suppose we have taken a very simple signal, a rectangular pulse. This is our input signal. We have to find against this input signal how actually the transistor switching or the practical transistor switching performance occurs. So this is the input signal. Suppose the highest value is of the voltage V1. The reference value in the middle is the 0. And this is time period 0 to capital T. And the lowest attainable voltage value is V2. This is the input which we have substitute. So at V2, transistor is cut off. At V2, transistor is at cutoff, and at V1, the transistor is at saturation. That we are assuming against a simple rectangular wave signal. Then we will try to see how the response of this transistor circuit, that means the output current IC with respect to the VI in voltage, actually behaves in a more or less transistor circuitry. So I will draw first. The drawing is a little tedious. Then we will come explaining one by one what each and every terms are defining. So if this is your input, और rather than इसको simple तरीके से draw करते हैं. This is output. This is the voltage value. We have already taken 0, capital T. This is extendable. अभी फिलहाल नहीं extend draw करते हैं. This is the output of the transistor switch. The output is the collector current as per this circuitry, which is being observed at the load position. So let me draw. थोड़ा बहुत इधर उधर हो सकता है. Sorry, सबसे बड़ी गलती कर दी, नीचे जगह नहीं रखा. To redraw. This is the maximum one. This is the next one. Let's draw one by one, then I will come explaining. Sorry, just redraw. Sorry, just redrawing. Give me a few more minutes. हाँ बताइए. क्या बोल रहे हो? हाँ, मेरे उम्र में पहुंच जाओ, आ जाएगा याद. या इस प्रोफेशन में भी आ जाओ. 40 साल में पहुंच जाओ, फिर बात करेंगे तुमसे. पहले ड्रॉ करके रखना चाहिए था. Fine. So this is your IC. this is the 100% of the IC usually. Withdrawing. This is usually 90% of the ICS or the saturation current. Since at the top it is a saturation one, so 0.1 ICS. CS stands for the saturation. This is usually the 10% of the saturation current. So this becomes, this portion usually known as TD. If you look carefully, the input pulse increases very sharply. The transition is fast on a same time period of time. But whenever it is applied to a transistor circuit with the practical limitation of the circuit components, because there are voltage sources, resistances, transistors, metallic wires, so the output never be such rectangular shape, rather than it becomes broadened, or instead of starting from this point it actually gets delayed up to certain time. So this portion is known as TD, the delay time. Up to this portion, the graph is rising. So this is known as the TR, or the rising time. And finally, when it reaches this point, the transistor eventually gets on. So your pulse, and after this TD and TR, it actually gets on. So T on is your TD and TR, up to which it gets it gets properly on. Then up to this period, it is almost, sorry, it's almost saturated, or almost making uh, a saturated value or stable value. So stable time, or TS is also known as a saturation time or storage time, basically up to which the energy get, sorry, the charges get stored within the system. After that, it starts get falling. So within this period, that means from here to here, the pulse actually gets falling. So that contributes to the falling time. And starting from this TS to this one, when it gets completely off, it actually contributes as a off time, T off time. So this is basically the response. Even against a pure rectangular pulse, the transistor circuit provide you uh, different time attributes to provide a completely flattened kind of a pulse shaped response or the output. So one by one, those attribution of the time, TD is the delay time, time that elapses during, time that elapses during delay together together the time together the time required for the current to rise %10 of its maximum value. That is your delay time, TD. Next one, TR, rise time. Time required for the current to rise from 10% to 90%. Time required by current rise from 10 to 90%. So that altogether provides the on time or turn on time T on, which is nothing but TD plus TR. Then it comes the storage time. Sometimes it is called stable time as well. Storage time, the interval elapses, the interval which elapses between the transition of the input waveform and the time when the current has dropped now the dropping has started, the current up to 90% of its maximum value. Next is the fall time. TF, time required for IC. Remember, I'm writing the small IC since we have now applied a small AC, small AC input to fall from 90% to 10% of its maximum value. And finally, it gets concluded with the turn off time T off, which is equals to your storage time plus fall time. So usually if we talk about any example in an NPN silicon transistor, just to give you an insight how small these timings are, this for an NPN silicon transistor, this TD is about 10 nanosecond, TS is about 40 nanosecond, TR is of 50 nanosecond, and TF is of 30 nanosecond. So you can see even after the delay time very small 10 nanosecond, the pulse actually get properly on. The on second rise time is quite high, 50 nanosecond. After that, it remains very short time, 40 nanosecond to be stable. and then it starts dropping 30 nanosecond. So those are the reasons for which or the contribution of the different contribution of the uh, 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 transistor switching times, which actually provides you how fast your transistor can act as a switch or how slow your transistor can act as a switch. Now automatically there are different reasons of this TR, T on, TF, all those which we will try to discuss, because once we get to know the reasons, then we can choose our design, because definitely our aim should be to design a switch as fast as possible. If you can narrow down your TD, TR, TS, all those things at the picosecond level or even femtosecond level, then a better switch provider you are. And totally, and basically the optical switches which are actually connected in the optical fiber communication, those switches are even faster than that, because those actually deals with the photon. So they have also used the switches, optical switches, not only about this transistor based switches. So nowadays it's and then only because if you reduce your switching times, then only more and more gigabit per second data rate you will be capable to provide to your vendors through your uh, organizations. So let's analyze one by one what are the different reasons of this, or different hindrance of behind this different times. The first one is delay time, which are responsible. Basically there are two factors. One is when the minority carriers may be brought to cross the emitter junction into the base, a time interval is always required where carriers can cross the base and reach the collector to produce the IC, because transistor output or switching output is what? Getting an output of collector current. How fast your carrier from emitter to reach collector, the simple principle of operation of transistor BJT, which we had discussed, that we have to make it much faster. There are reverse saturation currents as well. There are minority carriers, majority carriers, both, which have to take care of all those cases. So minority carriers, a time required. Yes,
So your voice is cracking.
Yes, sir.
I'm really sorry, but how can I help you? I'm really sorry. How can I help you? I mean, whatever connection I have, I'm able to provide with that. I will just write it down with a little bit of delay. You will get to see what I'm writing.
Yes.
I'm really sorry. Then just depend on my writing. I will try to explain in some other class. Just I will finish it then. Time is required charge up the emitter junction transition capacitance so that transistor may brought from cutoff to active region. The second point, a time interval is required where carriers can cross the base and reach the collector to produce IC. And the third, finally, some time is required for IC to rise to 10% of its maximum value. Basically, there are three contributing factors. One is the emitter junction capacitance, which contributes a time to require to charge up the emitter, because until and unless emitter will be properly charged up, it can't emit the proper electrons. A time interval for the carriers or the minority carriers to cross the base and reach the collector to produce IC. And finally, the IC to rise from its 10% to its maximum value. That are the uh, affecting factors for the delay time. Correspondingly, for the rise and fall time, if the base current step is used to separate the transistors or return it from saturation to cutoff, IC must traverse the active region. Whatever best design we can opt, it is very difficult to bypass the active region. So there will be some intervention of the active region, which actually gives the proper hindrance in the rise and fall time. Moreover, IC increases or decreases along an exponential curve whose time constant TR is given as which depends on the radio frequency and CC is the collector transition capacitance. One small portion to complete the topic, that is the storage time, the three which depends on the failure of the transistor to respond to the trailing edge of the input pulse for time interval Ts. at the saturation region due to excess minority carriers developed. So that more or less completes the design issues of a transistor as a switch. Remaining, there are few problems on the transistor as a switch as well as the active and saturation region, which we will start from the next class. Am I audible properly now?
Yes.
Yes, sir.
Uh, so we have done a very little bit of transistor switch or a transistor generalized circuitry, where you get to know how to know that how to know the active region, saturation region, all those things. There will be an assignment which I will give you in this weekend or by tomorrow. You have to simulate this circuitry for any available range of the transistor in your simulation package, whether it's multisim, whether it's PSpice, and you have to tell me the best suitable value for the VI, the IB minimum, and the RB maximum, or RB minimum or IB maximum or VB max to drive the transistor either in cutoff region or in the saturation region. You have to provide me the values, as well as you have to draw the corresponding output characteristics curve, which will show the transistor is driving with those values in the cutoff as well as in the saturation region. Understand? The assignment will come correspondingly, so you have to simulate through your simulation platform, and individually you have to show what kind of or who is getting the best values in designing a simple switch or a simple transistor as a switch. That ends this week's courses. Let's have the roll call first. Roll number 1. Roll number 1.